suppose then this is an edge-on view of a pane of glass, okay? And suppose we could see the actual silicon dioxide molecules that make up this pane of glass. And this one, that's supposed to represent them. And here comes a photon of light that got emitted somewhere in the universe, and it's been traveling through space, and it reaches right here. When that photon hits this very first atom out here on the edge of the pane of glass, that atom will absorb the energy. And now one of two things will happen. It may just absorb that energy, and then the electron kicks up, drops right back, and emits another photon. And if it does, how much energy will the new photon have compared to the original photon that caused the electron to be kicked up in the first place?
A little less.
Turns out it's the same amount. It turns out that they're not a frictional loss in this case. You end up with the photon that it emits is like a twin of the original. Okay? So that atom, the photon hits it, the atom absorbs and re-emits a twin photon. Then, suppose that photon traveled in the direction into the glass. It might travel a certain amount of distance before it comes to the next silicon dioxide atom. But when it gets to the next silicon dioxide atom, if it's positioned there, that photon can hit it. And what's going to happen when that photon hits that second molecule? Same thing. That second molecule gets excited, the electron kicks out to a higher level, and then it drops back. And when it drops back, what happens to the energy? It comes flying out in the form of a new photon. So how does that photon compare to the one that came into that molecule? It's a twin, and that one was a twin of our original one. So you guys get what I'm talking about with all the different twins? If I continue that chain reaction all the way through the pane of glass, finally over here on this edge, the last glass molecule, the last silicon dioxide molecule, when whatever twin is going to hit it, it hits it, it absorbs, falls back, re-emits. It emits a photon flying off out in this direction. Okay? How does this photon compare to that original one that came in on the glass on the other side? It's a twin. Now, is it the same photon? It's not the same photon, but it's just like the one that came in. Okay? Now, suppose your eye is sitting over here looking at this glass. And suppose this photon that came in was red. So over here, we had a red photon that hit right there. What do you see on this side? You see a red photon. And so we would say, well, this glass is transparent to red photons. Okay? So if a material is transparent, that's our model of what we think is happening. The atom hits, gets excited, re-emits. Hits, gets excited, re-emits. So you have this continuous chain reaction of the atoms absorbing light, re-emitting, absorbing, re-emitting. So how does the speed of light when it's in glass compare to the speed of light when it was out here in the air?
0.75.
Maybe. I don't know.
It was in the
But I like the fact that it's less. 0.75 is less than 1. Why would it be less in here than it is out here?
Because it takes them.
Well, you keep answering everything. Why is it less in here?
It has to go through more molecules to go at the same amount of space.
Yeah. While the light is actually traveling, it's traveling the same speed that it always does in vacuum, 3 times 10 to the 8th meters per second. But it takes a little bit of time for that molecule to excite and re-emit. And then the next one, it takes a little bit of time for that one to excite and re-emit. So while the speed of light actually has not changed, the effective speed of light, the average velocity as it travels through the glass, ends up being less than it was in the air. And actually in air, the same thing is going on, except air molecules are pretty far apart, and so there's a much bigger distance between when the molecule hits, between when the photon hits one, excites and re-emits, and when it hits the next. So the speed of light in air is almost the same as it is in a vacuum. And in a vacuum, that's when it would be moving the fastest, because it doesn't have any hit, excite, re-emit, hit, excite, re-emit. Now, let's change the situation a little bit. Oh yeah, question?
So like a vacuum, does it have to have some like hit and emit at the very beginning?
Well, the photon of light was originally produced by a moving charge somewhere.
Okay.
And that moving charge may have been in the sun, or it may have been in a star clear over on the other side of the galaxy.
Oh.
But that moving charge emitted a photon, and that photon is flying through space, and if it hits a molecule and excites it, that molecule will excite and then drop back and re-emit a twin photon.
Okay, I didn't know if like you had like if it had it got into
Okay. Now, yeah.
Is it always visible light? Or
No.
can it be-
No, this thing that I'm describing is true for all electromagnetic waves. We will learn again when we get into the quantum unit that some photons have higher energy than others, and like in the visible stuff, the blue or the violet light has the highest energy photons. The red red light has the lowest energy photons. But it's true whether they're visible light or invisible heat, infrared, gamma rays, whatever. Yes.
But things that might be, transparent to visible light might not be transparent to other types of
Yes,
waves.
exactly. In fact, that's where I'm going with this next part. So when I get this next piece in about the resonance, where resonance plays a role, then we can start talking about why some materials are transparent to some wavelengths of light, but not transparent to all wavelengths of light. All right, so now, I need to talk a little bit or refresh your memory on resonance, because I didn't have all of you in Physics A, and even the ones that I did have in Physics A, I don't know how much you still recall about the idea of resonance. So I'm going to be quiet for about a minute and just talk to the people at your group and share ideas. Just tell, what do you remember about the concept of resonance? What was it?
Is when it like interference is when it adds together.
When they interference when they have together and they will
You know, you could have destructive or constructive.
Interference is a principle of it. Interference, resonance is when all the interference is constructive.
When it's constructive interference.
It's all constructive. Yeah.
No, resonance is when it reflects back with the exact same wave pattern that it had. That's what it is.
That's not what it
Oh yeah,
says.
when waves,
I do not remember. Allison's class like 2 months ago.
I said this class a year ago.
No, it's
It's when-
All right, let me have your attention back.
It's vibrating in its natural frequency of
Can somebody give us an explanation of resonance and how they think of it, what it is? Okay.
I'm not entirely sure that this is right, but it's when the wave that like goes into it kind of is the exact same wave that goes back out, I guess. Like kind of just reflected backwards.
That's true. It depends on our situation. Like in what I was drawing before, the twin wave, or the twin photon that came out compared to the twin that came in, that can happen whether resonance occurs or not. So I need to polish the resonance idea a little bit, but I understand what you're saying. Skylar, and then I'll go here next.
I've kind of got two sides to it, but I think they work together. One thing with resonance is that all the interference is constructive, so it's building and getting stronger and stronger and stronger. And another idea is that it's being able to do that because it's whatever vibration is happening, it's when it's hitting an object, that object's natural tendency is to want to vibrate at that frequency.
Okay. I like that. And we'll talk that over in a minute. Zach,
It
something
was
to
kind
add?
of like, it was extending on what Ashley said, but like whenever you're passing a vibration or a wave through an object, and the object creates the same wave back, like the wavelength is the same as the length of the tube that you have whenever you send that sound or that sound wave into this tube, the tube will create the exact same sound wave back, but they will add together to create an even larger amount than what came.
Okay. Does that make sense to you, Dylan?
Sort of. That was kind of It's hard to say. I just kind of.
I never quite understood how you're supposed to, how you can know the frequency of something. Like every object has a specific frequency, right?
A natural frequency, right?
Other words.
So that means that there's a certain pitch that if you like play a sound, that noise will, or that the object will vibrate with that wave, or with that sound wave, and so make it louder essentially. I mean, it never really made sense to me because of instruments. Like if you have like a guitar, how then it would resonate with multiple frequencies. So,
It's a different.
Yeah, the force vibration, I understand where the confusion's coming in. But let's sort that out. First, the idea of natural frequency, that's an important thing. Everything, if it is disturbed, will vibrate at a natural frequency, okay? What I tend to think of is like a swing with a kid on it. So if we picture we have a kid hanging, a swing set here and a kid hanging on it, and you push, that swing set is going to vibrate at some natural frequency, okay? And if I come up and try and force it to vibrate at some other frequency, it's not going to work real well. The kid will still move. But if, for example, if the kid's hanging here and I come up and push thump, 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 they're not going to swing very high, even though I put a lot of energy into it. Because I was operating at this frequency, thump, 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 but the swing was operating at swing, swing, that frequency. And those two are different. So when I gave a push, it started the swing going, but when I pushed it the second time, it was still heading that way. So those two pushes might have added together and gave it a little bit bigger boost, but by the time I gave it the third push, it was heading back this way, and I just canceled out a bunch of my force. So my pushes sometimes add to the swing and sometimes cancel out, and I end up with no great motion, okay? Now, on the other hand, if I push exactly in time with the natural frequency, so if the natural frequency of the swing is swing, swing, and I come up and push exactly in that. I push, I wait for them to come back, I push again, wait for them to come back. My push is exactly the same frequency as the natural frequency of the swing. Now, all of the interference is constructive. It always makes it increase the amplitude, and so it gets bigger and bigger and bigger and bigger. With sound waves, we typically hear